Hi and welcome to another Unity 5 tutorial. This is an advanced tutorial and today I'm going to take a request from Mama Crow, who's posted some very lovely comments on my YouTube channel, so thank you very much for that. And they wanted to know about infinite terrains. So in this tutorial I'll show you how to create an infinite terrain. An infinite terrain is one that the computer generates as you walk along, and it means you can have your character walk forever and never run out of terrain. There's a lot of sort of issues that surround this as far as actually putting objects on the terrain, ensuring that they're going to be there after you've gone a long way away and keeping track of all those things. But we're actually going to look at just the landscape in this tutorial. Right, so the first thing we need to do is to open a new Unity project, which I've got here. And I've also imported the character controllers, which is under Assets, Import Package, and Characters. Now I've done that because I want to use the first person controller to wander around on the terrain. Right, so an infinite terrain needs to be made up with single blocks of landscape that you then tile next to each other. So the first thing I'm going to do is make just one of those blocks. Okay, so in the hierarchy, let's create a 3D object plane. So this is the default Unity plane that we're going to be using, and something to note, which is going to become very important later on, is this plane is actually 10 by 10. In the Minecraft tutorial, part 1, we used blocks, cubes, which are only of size 1. And therefore our whole landscape that we generated was based around the dimensions of 1 by 1 by 1 by 1. This is now going to be around dimensions of 10 by 10 by 10. Now you can create your own mesh in an external package that's bigger than this one, that's 10, but you'd have to update the code as well. Alright, so we've got our plane, and we're going to attach to this plane some code that's going to make it hilly. We're going to use the Perlin Noise function. Now, if you haven't learnt about Perlin Noise, I highly recommend you look at the Minecraft tutorial, part 1, where I go in depth into what Perlin Noise is. And rather than reiterate that here, it's best if you stop now, go back and have a look at what Perlin Noise is, and then come back to here. But in short language, Perlin Noise is a mathematical function that gives you smooth random values. Great for creating landscapes. Right, so we've got our plane. We're going to add some code onto it. So in the project, let's create new C# script. And we're going to call that generate terrain. And I'll just open that up. Okay, so here's our default script that we get, and I've got one I've already written, of course, in memory, so I'll just paste that in here for you to have a look at, and we'll go through it. So this script will be very familiar to you if you've done the Minecraft part 1. It's basically the same script. Let me just bring this line down so that you can see it. Just put it there. Okay, so we're using this math.f Perlin Noise function exactly the same way that we did in the Minecraft example. We also have a height scale and a detail scale that we need to implement to make sure that we get the correct amount of height and detail in our landscape. Okay, so now instead of looping around a two-dimensional grid and putting cubes in there, we're looping over the entire mesh, and we're lifting up each of the vertices. So we're taking the Y position of each of the vertices in the mesh, okay, and the mesh is taken from the object that we're going to attach this code onto, which is that plane. Now if I just quickly switch back to this plane, I'll just save this. Okay, now this plane, you can see all these little vertices here. We're going to grab each one of these and we're going to lift them up. And we lift them up using the Perlin Noise function to calculate the height. So if I just go back to the code, you can see there that the height, the Y, is set using the Perlin Noise function, taking its values from the X position of the vertex and the Z position of the vertex. Now we're also using the position of the plane itself in the world as the offset for the Perlin Noise function. This is important so that we don't have every plane that we create looking exactly the same. We want it to be seamless, so it has to join at the edges, but it has to continue on being sort of random and smooth as it goes. Again, refer to the Minecraft tutorial one on why this is so. Okay, so after we've updated the actual mesh, which we're doing, as you can see here, putting the vertices in, then we're setting the vertices that we've just calculated that are in this separate array, putting that back onto the mesh itself. Once we've done that, we need to recalculate the bounds of the mesh and the normals of the mesh because the whole thing's kind of changed. And if we don't do that, it will look really odd. And feel free to leave these two lines out if you want to see what happens. Okay, now once we've done that, we also need to add a mesh collider so we can walk around on the surface. So this is the code. And you might like to pause at this point if you're typing it in. All right, so I'm saving that, which I think I already did, but do it again. Okay, so let's grab this code and put it on to that plane. And then we'll press play. Okay, now you can see that Perlin Noise has been used on the surface of this plane. Now, because we have an offset in the position of the plane, if we have two planes next to each other, the Perlin Noise should be seamless but continue and not be the same. So let's take this plane, which has the code attached to it, and we're going to duplicate it, so Control D, and let's move it by 10 in the X direction so that we now have two planes that are next to each other. And they both have that code on it. So they're kind of smart planes. They look after their own Perlin Noise. Let's run this now. And we can see that our terrain meets very nicely on the seam. But the mountain range continues. And it's not exactly the same on both of these. And that's because of this positioning here. So let's just add another one and let's put it at 10 in the Z direction and run it again. So let's see what we get. We get a nice continuous landscape there. And you can see what we're aiming to do is build up a very large landscape made up of all these little tiny sections. All right, so before we continue, I'm now going to delete those other extra two planes out of here. This plane I'm going to make a prefab out of, drag it over into the assets. I'm going to call it a smart plane because it's got our code attached to it. And while I'm here, I might actually put a terrain image on it. So let's just drag in this grass that I've got left over from the Minecraft tutorial and drag it onto there, and just make sure that we update or apply any changes to the prefab and then delete that prefab. Okay. So let's create an empty game object in the hierarchy, which will be called landscape. And this is going to have the code on it that generates our infinite terrain. So we're going to create another C# file, and we'll call that generate infinite. And I'm going to attach that to our landscape. I know it's empty, but let's put it there anyway. All right. The next thing I'm going to do is bring in our character controller. So let's go into standard assets, which is where it lives if you've downloaded that package. First person controller, prefabs, and we want this FPS controller. So drag that into the hierarchy. Now, I'm going to ensure that we're at 0 in the X, 0 in the Z, and not sure, let's say 20. Let's put it there for the height of our controller, so that it's situated in the center of the terrain that's going to be created and above it. So the terrain is going to start around 0, 0. Okay, so let's go to our code now. Let's open up Generate Infinite, and you'll have this skeleton. I'm going to paste in what I've got so far. Okay, let me just put another closing bracket on there. Right, let's go to the top of this and just have a look at it. So the first thing we need to do is not only generate all of the tiles, but to keep track of them. Again, if you go back to the Minecraft tutorial in tutorial 2, the part 2 for that, it creates a class that needs to keep track of the object that's in the world, so the game object, as well as keeping an array of the game object tiles so that they can be deleted later on. And moved around and that type of thing. So in this case, I'm creating a class called tile, so that each one of our smart planes will be placed in a tile, which is here. And these are going to record their creation time as well. And I'll talk more about why this is important later on. So this is our constructor for the tile, where we give it a link to the actual game object that has been instantiated in the environment and also its creation time. All right, so here's our Generate Infinite class. And see if I can make this window a bit bigger. Might all fit in. Yep. Okay, so we've got 2 public exposed variables at the top here, both game objects. One is our smart plane, prefab, and the other is our player. We need to know where the player is in order to continually generate more terrain, which we'll look at in the second half of this. We also require a plane size so that we know where to put the next tile so that they match up nicely. So because they're size 10, each time you put down a new tile, you want it to be 10 away from the previous one. Just like we in Minecraft, where we put 1 next to 1 next to 1, it would all be in chunks of 1, whereas this is going to be 10. Now, the player themselves, the character, is going to be surrounded by terrain. And essentially, this value here is our radius of how many tiles are around the player in any particular direction. I've split this up as an X and a Z, which would allow you to have a deeper map than it is wide if you so wanted. This whole example is keeping them the same size. So I could have just had like a radius in here, I guess. But, you know, it's 10 by 10, so we'll just live with that for now. We then have a start position that we use to keep track of where the player is and where the player was. So as the player starts to move through the environment, we don't want to continually generate new terrain constantly around the player. It's just going to be too heavy. We have a terrain that's a certain size, and then when the player moves a certain distance from where they previously were, we then generate more terrain. So that when the player maybe walks 10 steps in one direction, then we make some more terrain. The reason being, again, is that we don't keep constantly generating terrain every update. It's just too heavy. Now, in the Minecraft tutorial, we used a three-dimensional matrix to keep track of all of the tiles in the world. In this one, we're going to use a hash table, which allows us to hold on to all those game objects and index them based on a name. And the name of the object is going to be generated according to its X and Z position. So that the tile at position 1050 is going to be called that, tile 1050. And then it allows us to find it easily later on. All right, so the start function. In the start function, we're going to loop a nested loop, which loops in the X and the Z using these two radius values we've got here, so that it creates a 2x2, not 2x2, but a two-dimensional ground plane made up of all these connecting planes. Okay, so each one you can see that we're creating the plane here, and then we're giving it a name, the tile, based on its X position and its Z position. Let's just make this window a bit bigger for you. Okay, and then we're creating a new tile. This is our class from above, which sets the tile game object, this here, and then gives it the update time, or the time that the tile was created, which we are setting outside that loop so that each tile created inside these loops has the same time. And then we're adding the tile to our hash table up here using this line here. Save that code and come back into Unity. And if we go to our landscape, in the hierarchy, we can now see that the plane and the player are exposed in the inspector. The player is our FPS controller, so we can drag that in there. And the plane is our smart plane that we created before, which is down here in the project. So I'll just drag that up and put it in there. Okay, so now we're ready to run and generate our landscape. Press play. And bingo, we have a landscape. The landscape isn't infinite at the moment. It's only 10 by 10 or whatever I had set in the code. Let me just have a look. Yeah, so actually 20 by 20. So it's got a radius around the player of 10, which is going to give you 20 by 20 tiles. Okay, so I'm just going to run it again, and I'll zoom out in the scene so you can see how huge that is. Now, it probably doesn't need to be this huge, because likely you're not going to want to see all the way to the end. I guess it depends on what you're creating. So by using the controls in the generate terrain code that's attached to the plane, the smart plane, you can modify what the height scale and the detail scale is of each plane's bumpiness. Okay. Right, so the next thing we need to do is to figure out where the player is and then make sure that terrain keeps getting generated in front of the player so that you cannot walk off the edge. So back in our generate infinite class, we're going to add the update function because it needs to check each update where the player is, and then if the player has moved a certain distance, we're going to update the terrain around them. So just after start, I'm going to drop this update function in, which looks quite long It's actually not compared to some of the ones we've already done before. So just bear with me with this. So here's our update function. The first thing we're going to do is determine how far the player has moved in the X and Z direction. If the player has moved more than one plane size, okay, so this is the plane size which we set up the beginning, where is it? Here, which is the size of the mesh, of the smart plane. Okay. So we take the player's current position in the X and the Z and find out the difference between where it is now and where it was. So start position is set right up at start to be the same position as the player. Okay, so this each update will tell us how far we've moved from our starting position. If we move in the X or the Z by either the plane size, then we need to update the tiles that are around us. Okay, so before we create a whole bunch of new tiles, we're going to generate the time that we're creating them. And we're going to use this time to delete any old tiles. So every time we generate a whole new batch of tiles, we will stamp it with a time. We can then go and look back through all of the tiles that exist in the environment, and any old ones we can actually remove, because if they're not with the current timestamp, they were generated before and they're now outside of the range of the player. Any tiles that were generated before that are inside of the range of the player, then we're going to update their timestamp. Okay, so the next thing we do to position the tiles themselves is to use the player's position. Okay, so before we generated our tiles around 0, 0, and they were 10 in size. Okay, so we put them 10, 20, 30, 40 in both the X and the Z directions. We're still going to do that, but we need to know where the player is in order to position the tiles around the player. But we can't have the exact position of the player because that's a float, and that just gets too messy using floats. So we're going to round the player's X and Z values off using the math.floor function. And we're going to, or I should say round down, we're going to round them down to the nearest 10 or the nearest plane size, because plane size is 10. So the way to round something down is to use math.floor. And if you want to round it down to the nearest 10 or 20 or 50 or whatever, you have to do a little bit of mathematics, which is basically to floor the number divided by the nearest whatever, so in this case 10, and then multiply it back up by that amount after you have floored it, and that will round it down to the nearest 10 plane size in the X and the Z, which gives us a nice clean position value for our tile, so that it will still be at a value of 10 when it's positioned. And we then see our familiar nested loops again going around the X and the Z, but instead of positioning these around 0, 0 in the center like we did in the start, we're now going to position them around the player's X and Z, or the rounded off player's X and Z value. So this is sort of the offset, so that every time we do this loop, it will create all of those tiles around the player. Okay, this next string is setting the name of the tile using our positions. And then what we're going to do is add all of these new tiles, or create these new tiles only if they don't already exist. So if there's like what we've got 20 by 20 tiles going on, 10 tiles radius around the player. And if you've only moved 10, chances are there's still a lot of tiles that are still relevant to the landscape that you can see. We don't want to recreate these. They've already been added to that hash table up in Start. So this line is saying if we've already made these tiles before, don't do it again. If we haven't, if they're not in that hash table, then they're new tiles. They're on the edge of our current landscape and we need to add them. So we create the tile, we instantiate our plane, we then give it a name, and by giving it this name, you'll see that come up in the inspector, and I'll show you that in a moment. It helps with a lot of debugging to know what tiles exist, what they're called, and that sort of thing. We're then going to create our new tile object using our new instantiated object and the new timestamp. Then we're adding that to our hash table. All right, continuing on. If the if this if statement fails, it means the tile does exist in our array, but we don't want to discount it. We want it to stay there because it's still a relevant tile. So we're updating its timestamp. So its creation time gets updated to the new time with all of these new ones. And then after that, we get rid of all of the old tiles using the old timestamp. So what I'm going to do first here before deleting the tiles is to create a new hash table that we will put all of our new tiles in. And then we loop around the old hash table, pull out each tile, check if its creation time is not equal to update time, so the time we've just created all these new tiles, which means it's old. So if this is true, the tile we've got hold of is an old tile. It's not inside the range that we're generating for the player. Therefore, we're going to destroy the game object out of the environment. So remember, the tile value is in the tile class and it's holding on to our game object. Now, if it is a tile we do want to keep, we're adding it to this new hash table here. So by the time this loop goes all the way around, this new hash table is only going to be left with our new tiles. Then once we've finished all of that, we've deleted all of the objects that we don't need anymore. We've got all of our new tiles in this new hash table. We're then going to set the old hash table or our global hash table that we're keeping track of the tiles to the new terrain so that we're essentially destroying the previous hash table and just putting new values into it. Now, the reason I'm not removing the tile from the hash table in here is that you can't do it. It won't let you. You get a not a syntax error. You actually get an error when you try and run it because a hash table, while you're looping through it, cannot delete an object. And if you go around deleting objects out of hash tables or somewhere else, that's nice. But what it does is it leaves what's called tombstones in the hash table. It leaves all these empty spaces. And then eventually the hash table becomes inefficient. By creating this new hash table here each time and copying it across into tiles, is that it gets re-indexed and therefore it keeps the whole thing nice and efficient. Okay, now once we've done all that, we then set our start pos value to the current player position. And then the player toddles off again. And once it becomes 10 away from start pos, this whole thing will start again, basically. All right, so that's the code. I'm just going to go up the top here and I'm going to reset these values here to 5, which is just a little bit smaller so we can see things on the screen. The plane hasn't changed. I'm just changing the radius of values. Let's save that and go back to our Unity and run it. All right, so here's our terrain. Let me just go down and zoom out on here so you can see what's going to happen as I start walking around in here. So I'm going to walk this way and eventually I'm going to get close enough that you can see the landscape in the scene moving. So what it's not actually moving, it's deleting a row of tiles from behind you and placing a whole bunch in front. And you can see, if you look in this game view, in the distance, the new tiles snapping into view. Okay, the other thing you can see in the hierarchy are all of our tiles, and you can see their names with their actual positions if you ever need to debug for them. Okay, so this is an infinite terrain, which is, what do we got, 10 by 10 tiles, so that's 100 tiles. There's only ever 100 tiles on the screen, which makes this really, really efficient. Now, what do we do about all of this snapping of the terrain into it is that we need to hide that happening. So to turn on the fog, if we go to window lighting, this is a very common trick used in games, is to use fog. Yes, it gives you a nice atmospheric effect, but it also hides a lot of things that are going on behind it. Now, if we bring in this fog, which doesn't cost us a lot processing wise to have on the screen, we can hide all of those planes snapping into view. So the fog is in this lighting window, under window. The fog setting is down here, and then we can just turn it on by ticking that box. And then we can play around with the color and also the density and the type of fog that it is. If you're interested in knowing what all of these others are, you can have a look. We're just going to use exponential squared. Have a look in the Unity manual. Now, I don't like grey. Let's try something a bit nicer. Sort of a light bluish kind of fog thing going on. That'll do. Doesn't matter for this example, I guess. Alright, so let's just run that. I think that window will stay on top. Oh no. Okay, so let's run it and let's have a look at our fog, which we can't really see on there. It's not thick enough. So I'll go back to our lighting window and put this up to 0.02. If you put it up to like 0.1, you're immediately in full fog. And just run it again. Okay, you can see that fog in the distance, which you can see from the difference in the texture here to what's going on in the back there. Whether or not it's going to hide that stuff snapping in, which it doesn't. Okay, so you have to go for a little walk to have a look. Still not thick enough. So I'll just change it to, let's see, 5. And run it. So you can immediately, it's just way thicker. And if we move, you can see it snapping in now, but the reason you can see it snapping in now is because there's no fog on the sky. If you're not familiar with fog or using it in your game, fog doesn't get projected onto a skybox. You can't have a skybox and have fog on. Not this type of fog. It's just a fact of life. So you need to turn off the skybox and give it a blue color as a solid. So first of all, let's get rid of this main camera, which we're not using because we're using the one that's attached to the first person controller. And let's find the camera. Okay, so it's on the first person character. Here's our skybox here. And we set that to solid color. As you can see, this changed immediately to the default Unity solid color, and we want that blue. So we'll select the eyedropper, and that's going to go and pick up any color it goes over the top of. Now that fog is back in the window lighting window, and it's here. So if I click that, it will transfer over to here and give us a background that is now the same color as the fog. Now when we run this, you'll see that the back of the landscape and the sky blend very nicely together. And you won't be able to see that environment snapping into view as you move. But you can walk forever. Okay, so that's an infinite terrain, and I hope you enjoyed that tutorial. If you've got any other requests, please send them through. You can put them on YouTube, or if you go to holistic3d.com, you can send me an email. I'll put the source code for this up on the tutorials section in the Holistic 3D website as well. Well, that's it for this tutorial. I hope that was helpful in teaching you how to create an infinite terrain in your games. Good luck with that.